Okay, let's get started. So welcome to another lecture as part of our ID 5130, the parallel scientific computing course. So in today's lecture we're going to learn about the parallel for directive. We actually kind of looked at it rather quickly in the last class. So we look at the parallel for directive and its limitations, okay, on what OpenMP can offer and what are the limitations. Okay, all right. So coming to the parallel for directive, we said that if you recollect the trapezoidal rule equations or the code, we only ended up looking at the C code. So I want to kind of focus a little bit on the Fortran code as well today. So for the trapezoidal rule, so that you can actually, some of you who are working on Fortran can kind of implement this thing. So if you recollect, in C we have this code for where we found the if you have started off with a serial code for trapezoidal rule, then all we have to do was essentially parallelize the for loop that was there in order to make it OpenMP parallel, right? That is as simple as that. Okay, so that means if you had a code, and in the C we had this width of each of the trapeziums as h equals b minus a by n, right? And where n is the number of trapeziums, and then we had the integral, which we can call it as total, is kind of computed using f of a plus f of b by 2. And then we had this for loop, right? So we had the for loop, and if we were to parallelize this thing, we wrote hash pragma OMP parallel for. Okay, so that's important, parallel for. Okay, and then we also have this keyword, that is num threads, which takes in some number of threads, in which case, in our case, this was stored in a variable called thread count. Okay, otherwise this is basically some number. And then we also have we have to also specify that the total is a reduction operator. So essentially plus is the reduction operation, and then total is the variable that needs to be reduced. Okay, so that means and then we have immediately following this pragma should be the for loop, right? Because this is a parallel for, so it should be for always, for I equals 1 to I less than n minus 1, so that is less than or equal to n minus 1, right? I plus plus, right? Because you have I equal to 0 is already covered in f of a, right? And then I equal to n is covered in f of b. Okay, all right. So then we have the for loop, and then we would simply write total plus equals, that is total equals total plus f of a plus I star h. Okay, so that's what we have. Of course, we need to add semicolons here as well, and then the for loop ends, and then we basically have to just multiply with total equals total star h. Okay, so that's what we had. So that was the C code. And coming to the Fortran, we said that it is kind of very similar, but I did not write it in the last lecture, so I thought I would kind of do it in today. So this is h equals b minus a by n. We don't need semicolons here. If you want, you can put them, but they're not required. So total equals f of a plus f of b by 2. That's the same thing. Then instead of a for loop, we have in Fortran what is known as the comment, right? Exclamation $OMP, that's your OpenMP, and then we are writing parallel for. So this is parallel for. I'm just writing in all caps just to distinguish. You can also write in lowercase because it's case insensitive. Okay, and then we have num threads, and then the variable whatever we give, and then we basically have the reduction operator. Basically it's plus colon total. Okay, so that's what we have. And then we have immediately sorry, this should be not parallel for, this should be parallel do, right? This should be parallel do. Okay, and then immediately following this we would have the do loop. Okay, so do I equals 1, or rather it will be like 2 to n minus 1. Okay, because your 1 goes into, it's always from 1 to n, so your 2 to n minus 1. And then if you want optional, you can give 1. This is basically the increment this is like I equal to I plus 1. Okay, if you ignore this, this will be taken as automatically as 1. Okay, so that is start index, final index, and then increment I equals 2 to n minus 1, and then we have our total equals total plus f of a plus I times h. Okay, that's the same as before, and then you would do an and do. Okay, and then finally, once the totaling is done, you would say total equals total star h. That's basically multiplying with the step size, and then we also need to add exclamation dollar OMP and parallel 2. Okay, fine. So essentially that's what we have. So that is your code for do loop, okay, or OpenMP do loop, which you can use in the trapezoidal rule. Okay, now this is great because this is very nice, because if you just have to kind of use a for loop or a do loop in your code, you can use whatever way we have described here and then easily parallelize your code. Okay. So as we discussed in the last class, if the code you're working with, if it is only has a very big for loop, then all you have to do is just parallelize that and you're done with parallelizing your code. However, if you have several for loops, then what you can do is you can incrementally parallelize your code by parallelizing each and every for loop and so on, right? Okay, so that is also very easy. Now it may appear that okay, it is very easy, however it is not as easy as it appears to be. There are several caveats that we have to look at. Okay, so let us look at these caveats. The first thing is your OpenMP. Okay, the first one is OpenMP will only parallelize for loops. Okay, so OpenMP will only parallelize for or do loops. Okay, it will not parallelize do while or while loops. Okay, well, that may not seem to be a big problem, because you may be thinking, well, if it doesn't parallelize do while loop or while loop, it doesn't kind of prevent me from recasting your do loop into a for loop, right? Well, that means you may be tempted to write one of your kind of replace your do loops or while loop or a do while loop as an infinite for loop, right? You just kind of give an infinite for loop, and you may say that, well, I would like to, because OpenMP parallelizes the for loops, I would write it this way. Well, that is not true, because OpenMP would not even parallelize these kind of for loops where the where there is the indices are not known a priori. Okay, so indices are not known a priori. That means if OpenMP cannot determine okay the length of the loop, okay, or the number of iterations in a particular loop, okay, then it won't be able to parallelize it. Okay, then it won't be able to parallelize the for loop. Okay, that means actually if you write something like this, okay, if you write something like an infinite loop here, OpenMP will actually give an error at the compilation. Okay, it will give an error that I don't know what will be the values of the indices, or what will be the extent, that it has to parallelize. Okay, so that makes sense, because OpenMP would like to kind of break this for loop, right, among the threads, right? So basically it has to kind of partition the for loop among the threads, right? Because now I is a private variable where I is the also the loop index, right? So it's a private variable, so it has to know how many what will be the extent of I that it has to put in thread 0 and how many it has to put in thread 1 and thread 2 and so on, all the way to number of threads or number of procs that we have p. Okay, so that it should know. As a result, it would kind of give you an error at the compile time that I don't know what are the indices, and as a result I cannot parallelize this, so you have to fix that error. Okay, all right. So what is the other limitation? Other limitation is that if you have a proper for loop that is defined, let's say you have for equal to for I equals 1, I less than n, I plus plus, and then you do something, and then inside if you have, let's say, a break statement, okay, or let's say you have a return statement. Now if we have something like this, then we may be saying, well, I have everything proper here, I have defined the extents and it should know, but the problem here is that this will also kind of complain or also throw an error because of the break and the return statements we have. So basically these are making this part of the structured block a not structured block anymore, right? So basically because there is a point of exit, so this is basically a point of exit out of the loop which is not allowed, which is doesn't fall into the so basically this is not a structured block. Okay, so as a result, OpenMP would still complain that when you try to compile it, that this is not a structured block and the break and return statement should not be there in the for loop. Okay, so that is also one more limitation of using a for loop. Well, okay, if that is the case, then OpenMP will only kind of parallelize. So OpenMP will parallelize for loops that are only in the standard form, okay, in the standard form, or we could say in the canonical form. Okay, now what is that? That is very simple. That is the simplest for loop you have learned. So basically you have for I equals start I, this could be now I less than or equal to, this could be I less than end, or I less than or equal to end, or I greater than end, or I greater than or equal to end, depending on the value it takes. And then this can, all the values it can have is I plus plus, I minus, minus minus, plus plus I, minus minus I, and it can also of course take, if you have I equals I plus some increment, okay, where increment is an integer, fine, and also I minus increment, that is also allowed, right? That means this is basically the standard form, right? So this is the standard form which OpenMP will parallelize. Now only thing is that now there are of course more conditions on this thing. So the conditions are that your start index, end index, and also the increment that you are specifying these should not be modified in the code. Okay, they should not be modified in the body. They should be set to be constant. Okay, should not be modified in the body at run. Okay, so essentially they have to be fixed. They have to be constant. They should not be modified in the body. So if you have a for loop like that, then OpenMP will parallelize that without any complaints. Okay, so now these restrictions basically allow your OpenMP compiler to determine the number of iterations at runtime prior to the execution of the loop. Okay, so this will basically, all these restrictions will allow OpenMP to kind of calculate the number of iterations at runtime, okay, at runtime prior to the execution of the loop. Fine, so that is kind of very much required. All right, so let us see if actually OpenMP does it really actually complain or not, whatever we have learned. by looking at a small program which I say program for loop exceptions. Okay, so I have basically a small C code here where I define n equal 50, and then we have our regular main program which is taking 2 arguments and printing if it is doing the error checking here. Okay, so that is the error checking part. And then what I have is we also have an integer array A which takes 50 elements, and then we have some key I and thread count. Okay, so thread count is used here, and then I is the loop index variable. And then we have basically we are filling some data. So I have hash pragma OMP parallel for num thread. So this is a parallel for directive, so it should be always followed by a for loop which is for I equals 0, I less than ni plus plus, or I equal to I plus 1. Okay, so I have this is I plus plus. We could test the I equal to I plus 1 as well. And then A of I equals I square. Okay, so I just fill in some data. Okay, so then I also fill in some key here. Okay, so let us say this is not required right now. Okay, so I would just say comment this part. Okay, I would just comment this part. Fine, so basically we fill in something here. Now I would say I would just try to compile this one. So this should work as it is. So this is GCC minus f OpenMP program for loop exceptions, and I don't have math.h, right? Oh, I do have math.h. Okay, minus lm. Okay, then I have dot slash a dot dot. I say 4. It has done something. It's not printing anything, so it compiled. Now let me basically just replace this for loop. Okay, just replace this for loop. Shift and W with for. Okay, with an infinite for loop. So that means compile. Of course, it gives an error now. It says for colon, it says error, expected iteration declaration or initialization before colon. Okay, so that is actually only coming from OpenMP, right? So if let's say now I have all the error checking in place, so this program should also compile without OpenMP. So I would do that just to make sure that this error is being thrown because we are using OpenMP and not because of just the C compiler. So I would just compile this without the OpenMP call, so it just compiles. Of course, now when I run it, it will just go into it should go into infinite loop, right? Yeah, I mean essentially. So okay, I have to give it one executable 5. So it now it just went into infinite loop and segmentation fault because now it tried to go for I which is more than 50 and it has given a segmentation fault because there is no memory after 50. Okay, all right, so that makes sense. Now let me compile again with the f OpenMP. It gives this error. Okay, all right, so that is fine. Then I would again put back the previous one here. Okay, now let me show that if you were to have, let's say, a kind of a search operation, let's say we have a linear search in which I have a key that we have to find. Let's say the key is, so once we fill some data, okay, I set some key is some 5 plus 5 square. Now I want to search that for that key value in the loop again. So I have another parallel for, that is hash pragma OMP parallel for, and then we loop over all the data, and then if a of I equals key, we want it to break. Okay, now we know that this may not really work with OpenMP may not like this because this is basically not a structured block of code, right? Because of the exit, because of the break. So if I try to compile this, it says that okay, it says break statement used with OpenMP for loop. Okay, it kind of tells you this is the error, so you can kind of fix it. So of course there is only one exception to this. The exception is that you cannot have break or return, but if you have an exit, OpenMP would not comply. So that is the sole exception to the for loop or to have a structured block with an exit statement. Okay, so if I compile this, it would do. Okay, that means of course, but it will not have the I data anyway. So if I do dot slash dot 4 or something, it prints, it kind of does and found the key location at I equals 0, but that's not correct. So but it does not comply. Okay, but if I have rather a return statement or a break statement, it will not form a. Okay, so it says error invalid branch to or from OpenMP structured block. So that structured block, it's not a structured block anymore because there is an extra exit that is being set up. Okay, so those are the now limitations of the for loop. Okay, now that is not the only one. We have more coming up. So the other one is known as the data dependencies. So let us go back and kind of make it a break statement, and then let me just comment these things because we may not use it right now. Okay, so that's kind of for this. Okay, so the other limitations that come are known as the data dependencies. Okay, so what is a data dependency? So let's say if you have a kind of a for loop that doesn't satisfy whatever is the restrictions we have set, then OpenMP simply gives you a compilation error, which is fine, right? Which is not a problem, because until you fix the compilation error, you would not be able to proceed. As a result, there is no chance that you will get wrong results because you are unable to run the code itself, right? Whereas there is a more serious problem. The serious problem comes because of the data dependencies, in which OpenMP will not warn you, okay? Rather, it will simply execute whatever you have given and happily produce wrong results because of the mistake in the code, okay, or because of the mistake in the way parallelization is being done. Okay, so in order to look at this, let us take an example of the Fibonacci series. Okay, try to kind of parallelize this using OpenMP. As you know, Fibonacci series is basically you have 1, 1, it will kind of add the previous two numbers to obtain the next number. So that is 1 plus 1 is 2, 1 plus 2 is 3, 5, 8, 13, and so on, right? 21 and so on. So that is the Fibonacci sequence. So let us try to parallelize this using OpenMP, using a parallel for, and see what kind of results do we get. Okay. So let me open program. This is program dependencies.c. Okay. Okay, so similar to before, we have now all the standard libraries included: stdio.h, stdlib.h, math.h, and openmp.h. And then I define now hash define n equals 20. So basically we have 20 values in the array, and then basically we want to compute the first 20 Fibonacci numbers. And I'm also defining an integer array, that is FIB, that stands for Fibonacci numbers. Okay, and then we kind of initialize all of them to 0. Okay, then we have the standard command line arguments. Then we initialize the first two Fibonacci numbers, Fibonacci 0 and 1, both to be 1 and 1. Okay, so that's what we have done. Then we have this parallel for loop. Okay, let me put it down. Oh, sorry. Okay, so parallel for loop, where we have hash pragma OMP parallel for. Okay, num threads thread count. Okay, so this is now we have already filled in what is 0 and 1 for Fibonacci. So we have to start from the second value and go until all the way to n minus 1, right? Because if you define an array for up to n in C, you have 0 to n minus 1 are the data entries. That means and you basically have Fibonacci of I equals Fibonacci of I minus 1 plus Fibonacci of I minus 2, right? So we have essentially take the previous two values and then add them up to find the current value. That's what Fibonacci series does. And then we have for I equals 0, I less than n, I plus plus. Here I'm printing all the Fibonacci numbers one after the other. That's all I'm doing. Okay, so let us say we have these 20 first 20 Fibonacci numbers, or let me make it first 10 to make it more interesting. Okay, so we just have 10 and then I say gcc minus f openmp. So I can even compile this without OpenMP, right? So program dependencies.c, that's it, it compiles, /error, I'll just give some number, it doesn't anyway matter. Okay, it has computed 1, 1, 2, 3, 5, 8, 13, 21, 34, those are correct, and that is basically computed by your serial code. Okay, now I'll say gcc minus f openmp, program dependencies, minus lm if it is required. I think it's not required at the moment. Okay, compile it, and then /error, run it with two processes. Okay, this seems to be working perfectly fine, right? So this seems to be working perfectly fine. 2, I did run it a few times, it seems to be working fine. Now I'll make it maybe 4. So there is a problem. So if it doesn't run with 4, okay, that's because maybe our 10 is not used. Okay, let me make it 20. Okay, then I'll compile it again, and then I'll run with 2. Okay, we got some numbers. I'll run it with 4. Okay, now there is a problem again, because 20 is now divisible by 4. It should have done properly. Well, it doesn't matter. Even if it is not divisible, OpenMP will actually take care of adjusting the loop extent, so it should still be fine. So it should have been actually running even with 10 and 4. Okay, so now we see that there are some zeros here, right? So there are some zeros coming up here. Now this is happening. If I run it with, let's say, 2, it seems to be fine. If I run it with 4, it's giving now more zeros. It's not consistent, right? Earlier when I have run, it's kind of going all the way here, and then it has given some zeros, and now it's giving more zeros. Now this is happening because of the dependencies that we have. So that means our Fibonacci I is kind of dependent on I minus 1 and I minus 2. As a result, basically this is called loop carry dependence. Okay, this is called loop carry dependence because in the loop, these iterations, we call these as, let's say, if you call the I equal to I less than n, we call this, let's say, as the iterations. Then the number of iterations are now split between the processes, right? If you have, let's say, 20 and 4 processes, each processor will get 5 I's, right? 5 array elements to work with. Now what's happening is that if the previous thread is fast enough and is able to compute all the Fibonacci numbers, then the next thread, when before it starts, if these are already filled, then it is able to calculate it correctly. But if the previous threads have not finished and the last thread has already started, then we end up with zeros here, because it is basically taking the initial value we have filled for fib of n array, and it's just adding all the zeros. So that is what is happening here. Okay, so this kind of thing is known as it is called loop carry dependence. Okay, loop carry dependence. That means the data or in the loop we have some elements that depend on or that depend on read write of other elements that are carried out in a different iteration. Okay, that means the elements in one iteration depend on the values of elements of another iteration. Okay, that is the problem. So that is known as loop carry dependence. That means and OpenMP did not warn us. You remember, we were able to successfully compile and run it as well, and happily get wrong result as well. So that means so this is the standard behavior. So basically OpenMP does not check for dependence, okay, among iterations. So it is the responsibility of the programmer to check and identify and fix all the dependencies. Okay, that means we should look for loops in which the results of one iteration or more iterations depend on other iterations. Okay, so that's what we have to check for. In general, OpenMP cannot correctly parallelize dependency loops. Okay, so that's what we have to check and see if we can parallelize it correctly, otherwise we won't be able to do it. Okay, so that means then how do we fix this problem? Maybe that is something for you to think. Okay, how do we calculate Fibonacci numbers in parallel using OpenMP? Fine, then let us see Okay, so that means that we have kind of looked at what is the loop carry dependence. There is other dependence known as the data dependence. So data dependency is, for example, let's say we have a loop. Okay, that means for I equals 0, I less than n, I plus plus, and then I have some variable here. Let's say x of I. We are filling it as some a plus I star h, and we have y of I equal to some sine of x of I divided by x of I x of I. Okay, so something like this. All right, so this means here we have our y of I kind of depends on x of I. Okay, so this kind of dependency is known as data dependency, and such a data dependency, if we have, is at least in this particular example where y of I depends on x of I. So we basically are referring to I here as well as I here. So where both i's kind of belong to the same thread, right? Because in this I equal to 0 to n, maybe 0, 1, 2 all the way to essentially n by p will belong to thread 0, right? And similarly 0 n by p plus 1 all the way to 2n by p will belong to t1, and so on. So as a result, if there is an I that kind of depends on whatever it belongs to the same thread, then there is no problem, and as a result such kind of data dependency is not a problem. Okay, but if you have again dependency on x of I minus 1, x of I plus 1, and so on, then that's basically will become a not only a data dependency but also a loop carry dependence, and that will again create a problem just like what we saw in the Fibonacci series example. Okay, so that means we need to detect these things and try to fix them, okay, if there is a problem. And how do we detect them? So to detect loop carry dependence, we should kind of concern ourselves by looking at what in the loop body, what elements, what variables are being updated. Okay, so basically look for variables that are updated, that means that are written right in the loop body, and then we should look for variables essentially that are written or read in one iteration and are written in the another iteration. So basically variables that are read or written in one iteration. Okay, here by iteration we mean that we are looking at basically I. Okay, so the values of I and written in another iteration. Okay, so such things are of problem. Okay, that is what we need to look for. All right, so basically now we have looked at the data dependency and the loop carry dependence. Let us try to kind of have an example of calculation of estimate the value of pi and see if we can have essentially explain our loop carried and data dependencies using this. Okay, or essentially see what all can we learn about this. All right, so let us take an example of calculating pi. So in order to calculate this, we will use the series expansion for tan inverse of x. Okay, so tan inverse x is x minus x cubed by 3 plus x to the pi 5 by 5 minus x to the 7 by 7 plus and so on. So you plug in x equals 1. Okay, so tan inverse 1 is basically pi by 4. So that's going to give you 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 all the way. Then you can calculate what is pi from this series expansion. Okay, so essentially pi equals 4 times this value, 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. So if you were to write this as a series expansion, this is 4 times, you have sigma some k equals 0 to infinite. Of course we will take some number n, and then we have minus 1 to the k, right? That basically gives you this alternating plus minus, and then in the denominator we have 2k plus 1, right? Basically you have odd numbers to come. So that's your expansion for estimate for pi by using some loop. Okay, and the loop will run from k equal to 0 to n, and then we would have this factor, and all of those will have to be summed up. Okay, so basically we have a sign variable which will take care of plus or minus depending on the iteration, and then that has to be divided by the loop carried value 2k plus 1, and all these things to be added to calculate what is the sum. Okay, so that is how we will write the program for this using OpenMP. Okay, and see if we can kind of look at the dependency within the loop variables. Okay, so let me kind of pull up this code. This is program pi.c. Okay, so just like before, we have all the regular libraries header files included. Then I define hash define n equals 1000. So this is kind of close to infinite. That is kind of what is enough for this particular problem. And then we have int argc, argv, and I also defined sign, which is 1.0, and sum equal to 0. And then this pi value would be the essentially the approximate value to be calculated, okay, using this series expansion. All right, then we have, of course, our regular argc equals 2, all these things. Okay, now comes the main part. So basically we have a for loop that is for k equals 0, k less than, and k plus plus. Okay, that is basically your this summation or for loop. Okay, and then we also have hash pragma OMP parallel for num threads thread count. Okay, I would remove. Okay, and then we have this reduction plus equals plus colon sum, because now we know that we have already know that sum should be a reduction variable, and if there were a function call here or something like that, we don't want that to be parallelized. As a result, only sum will be made a shared variable, of course, because we have said that this is a reduction operator. So the shared variable sum, because it is declared before, right, it's kind of declared before, right, it's declared here. So this will be made a shared variable, and private variables for each thread will be created. All of them will be used when this for loop is iterated, and then once the for loop ends, all those sum values will be, I mean, here itself after the after each calculations, they will be again added to the using a critical statement, right? Essentially they will be added in a mutually exclusive way. Okay, so we have sum plus equals sign, that basically takes care of plus 1 or minus 1 divided by 2k plus 1. That's what we have written here, right? Now sign, of course, has to change each time, so sign equals minus of sign, and then once we are done, we will multiply with 4.0, that is here. Okay, so that's what it is, and then approximate value of pi is such and such. Okay, so that is a nice simple program. So let us try to compile this. This is GCC. Let us try to again compile in the serial and see what is the value we get for pi. Okay, so this is /a.out. We need to give some command line, second command line argument. So value of pi is 3.140593. Doesn't seem to be too bad. So this is what is the correct value with 1000 values that we have computed. Now let me do it with fopenmp. Okay, program pi.c, compile /a.out. Let us use 2 threads. Okay, we got decent result. It's matching with the serial. That's nice. Let us use 4 threads. 1000 is divisible by 4. Okay, /a.out. Let's say 10 threads. Okay, this is not good. We got a minus. This is not good. /a.out. Let's say 4.38 something. So this basically the output is now unpredictable, right? It's kind of non-deterministic. This is happening because there is a bug in the code, and we can easily spot it. That is nothing but because k itself is given to be 0 to n. So this basically will lead to basically the threads will share the for loop, right? Essentially threads will work in parallel. As a result, out of the 1000, let's say when you are running with 4, approximately OpenMP might be assigning first 250 to one thread, next 250 to another thread, and so on. Okay, so as a result, what is happening is that and what about this sign? The sign is basically is it a shared variable or a private variable? Because sign is declared before the hash pragma OMP parallel, this will be a shared variable, right? So this is a shared variable. As a result, sign is updated by some thread somewhere, and then some other thread is taking it to be different value, and as a result the series is kind of getting mixed up, and that's why we're getting the minus value and plus value and all of the different values. Okay, that seems to be fine. That means we cannot compute it with this kind of alternating values. So why not update the value of sign itself? Okay, so let me basically make a copy of this. and then also make a save this, comment it for later. Okay, so I've just made another copy of the same for loop, and then instead of alternating the sign, I would directly calculate it depending on whether it is even or odd, right? Because our if it is odd, it should be plus. If it is even, it should be minus, right? So that's what we have. So let me make it as with if it is even, let us make it to be a minus value, and if it is odd, let us make it to be a positive value, right? Okay, that means if it is divisible by 2, okay, and then you have the 0 as well. Okay, so let me make it that. Okay, if I start counting from 0, so 0, 1, 2, so that means your 1 is your odd number. Okay, so that means I would say if the iteration is modulus 2 equal to 0, right, then what we have is sign equals 1.0, else, okay, I need to put a semicolon here, else sign equals minus 1.0. I don't need end if this is C. Okay, so that means, and then we have the sum equals sum plus sign of 2k, sign divided by 2k plus 1. Okay, that seems fine, right? So that's what we have. Now there is no problem, because now if it is not tied to the variable yet, right? So it is basically, if it is even or if it is odd, it will be automatically take care, and then it should work. All right, so let's compile again. That's the compilation. /a.out. 1 works perfectly fine. 2 fine. 4 4 is not good, right? It's 3.45. okay, that means there is still some problem. 5 something else. 10, okay, again it's kind of correct. So basically again there is some issue here. Now the issue is that essentially what we just discussed, right? Sign is basically still a shared variable. So what's happening is one of the threads is basically updating it to be +1 or -1, and then the other thread, when it comes, it's kind of using it before what it updates this value, it is kind of changed by some other thread. As a result, this is getting a non-deterministic value. So that means we need to make sign as not a shared variable, but we need to make it as a private variable. And OpenMP offers a very simple alternative, that is called, we can just define what is the variable, the scope of the variable. Okay, so it can be changed with the explicit statements like this, and we can say private sign. Okay, that means OpenMP is going to create a private variable sign for each thread, and it's going to use them for that particular thread, and it's going to update it with these values, and then it's going to use it. As a result, there should be no problem. Okay, so I have declared this. You can do the same thing in Fortran as well. Okay, no compilation errors. 5 fine, 10 perfectly fine, 2 20, I think it's working. Okay, so that means basically what we have is we just need to make the sign to be a private variable. Now what will be the scope for private variables? So the private variable, or what will be the initialized value? So private variable, inside the loop, it will not be initialized to any value. So that means you have to give some value before you use it. Okay, and then after the loop, again it will have a undefined or a non-deterministic value. Okay, so it doesn't have any value after the loop. So that means you have to, if you have to use sign after this, you still have to set it. Okay, because it can come from any of these threads. Okay, so that is how we use this extra clause called private, which basically defines the scope for the default shared scope for sign. It can be changed by using the private clause here. Okay, and we will see a few more things on the similar lines maybe in the next lecture or so. All right, so for now I'm going to stop here. Whatever we have discussed, you can also do it with Fortran. Okay, all right, so I'm going to stop for today. We will catch up in the next lecture. Okay, thank you.